December 16th, 1944, 05:30 hours. The Ruhr River, Germany. Lieutenant Karl Hoffmann pressed his binoculars against frozen concrete, watching the American side of the river through the pre-dawn darkness. Behind him, 140 veterans of the 7th Panzer Division occupied positions in what had been a sugar refinery before Allied artillery turned it into a maze of shattered walls and excellent firing angles. The Americans had been probing the river for 3 days, losing men to machine gun fire every time they approached the waterline. Hoffmann's superiors had been explicit in their briefing. The Ruhr represented Germany's last natural barrier before the Rhine. Hold it for 2 weeks, and winter weather would freeze Allied momentum until spring. The mathematics seemed simple enough. The river was 180 feet wide at this crossing point. Current speed averaged 4 miles per hour, swollen by December rains. Water temperature hovered at 34 degrees Fahrenheit, cold enough to incapacitate a man in 6 minutes. But what made Hoffmann's position truly impregnable was German intelligence on American engineering doctrine. According to captured field manuals and interrogation reports, constructing a tactical bridge capable of supporting 35-ton Sherman tanks across a river this wide required a minimum of 72 hours under ideal conditions. The Americans would need specialized equipment, extensive preparation, and most critically, time that German artillery and machine guns would never allow them. Hoffmann had studied engineering at Technical University of Berlin before the war. He understood load calculations, stress distributions, and the physics of bridge construction. The American Bailey bridge system, while clever in its modular design, still required precise assembly, careful positioning, and methodical construction that was fundamentally incompatible with combat conditions. His education and 5 years of military experience told him the same thing. The Ruhr was uncrossable until the Americans secured both banks, a process that would take weeks of bloody fighting. At 06:15, American artillery opened fire. Not the usual probing shots, but a concentrated barrage that walked across German positions with methodical precision. Hoffmann pulled back from his observation post as 105mm shells cratered the refinery's western wall. The bombardment lasted 17 minutes, longer than previous attacks, suggesting something significant was about to happen. When the shelling stopped, Hoffmann returned to his position. Through clearing smoke, he could see American infantry moving toward the riverbank under covering fire from machine guns positioned in the ruins of a church. Standard reconnaissance behavior, he thought. They would probe the defenses, take casualties, and withdraw to plan a proper assault that would come days or weeks later. But then he saw the trucks, dozens of them, moving through the American lines with purpose that seemed inconsistent with reconnaissance operations. These weren't supply vehicles making routine deliveries. They were engineer trucks, painted in the distinctive markings of the 291st Engineer Combat Battalion, carrying loads covered by canvas tarps that obscured their exact cargo. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The American engineering doctrine that Hoffmann had studied at university was based on German military principles that had dominated European warfare since the Franco-Prussian War. Engineering was a deliberate science, requiring careful planning, extensive preparation, and methodical execution. Bridges were constructed by specialists using precise calculations and standardized procedures that minimized risk while maximizing structural integrity. This doctrine had served Germany well through 2 world wars. German engineers built bridges that lasted for decades, designed fortifications that withstood months of bombardment, and created infrastructure that supported entire army groups. The approach emphasized quality over speed, permanence over expediency, and professional expertise over improvisation. American engineering training, according to German intelligence assessments, followed similar principles. West Point graduates studied the same structural engineering texts used at German military academies. American field manuals translated German construction procedures with minimal modification. The assumption throughout German military planning was that American engineers, despite their industrial advantages, would require similar timeframes for similar tasks. The Bailey Bridge system had been introduced by British forces in 1943, and German engineers had studied captured examples with professional interest. The design was genuinely innovative, using prefabricated steel panels that could be assembled without heavy machinery. Each panel weighed 570 pounds, light enough for 6 men to carry, strong enough to support tank traffic when properly assembled. But the system's modular design didn't eliminate the fundamental constraints of bridge construction. Panels still needed to be positioned precisely, connected securely, and tested thoroughly before vehicle traffic could cross safely. German engineering calculations suggested that even under ideal conditions, a Bailey Bridge spanning 180 feet would require 48 to 72 hours of construction time. Those calculations assumed trained crews working without enemy interference, adequate lighting, favorable weather, and proper equipment positioning. Combat conditions would extend construction times significantly, potentially doubling or tripling the theoretical minimum. This is why German defensive doctrine treated major rivers as barriers that could be held with relatively modest forces. The time required for enemy bridge construction provided days or weeks of warning before armor could cross. Hoffmann's defensive position had been selected with these principles in mind. The sugar refinery provided excellent observation of both riverbanks, allowing German artillery spotters to call fire on any American construction attempt. Machine gun positions covered every potential assembly area where Americans might stage bridging equipment. Anti-tank guns were positioned to engage any vehicle attempting to cross a completed bridge. The position had been prepared over 3 weeks by combat engineers from Organisation TOT, the same construction group that had built Atlantic Wall fortifications. They had calculated firing angles, constructed reinforced observation posts, and established communication lines that connected every defensive position into a coordinated system. This wasn't improvised defense, it was scientific fortification based on centuries of European military engineering tradition. Behind the refinery, German reserves waited in carefully prepared positions. 2 companies of Panzer Grenadiers occupied trenches that allowed rapid response to any breakthrough attempt. Artillery batteries were pre-registered on every likely American assembly area, ready to deliver concentrated fire within minutes of receiving targeting data. The entire defensive system was designed around one assumption. Americans would need days to bridge the Ruhr, providing ample time for German forces to mass and counterattack. This assumption was based on more than just engineering calculations. It was rooted in fundamental beliefs about how modern warfare operated. Armies moved at predictable speeds, constrained by logistics, terrain, and the physical limits of equipment. Bridges were built according to established procedures that couldn't be rushed, without catastrophic failure. Combat engineers were specialists who required specific conditions to perform their missions effectively. German military culture emphasized these principles through every level of training and doctrine. Patience was a virtue in defensive warfare. Careful preparation defeated hasty improvisation. Professional expertise trumped American industrial enthusiasm. These weren't just tactical concepts, they were articles of faith supported by centuries of Prussian military tradition and validated by years of successful combat operations. The irony was that German intelligence had actually documented American engineering capabilities with reasonable accuracy. Reports from Normandy described American engineers building bridges under fire, repairing roads while under artillery bombardment, and generally demonstrating impressive technical competence. But German analysts had interpreted this data through the lens of their own assumptions about how engineering had to, say, work. Fast construction was attributed to overwhelming material superiority rather than different doctrinal approaches. American willingness to work under fire was seen as recklessness rather than calculated risk acceptance. The possibility that American engineers might have developed fundamentally different methods for accomplishing the same tasks never seriously entered German planning calculations. Lieutenant Wilhelm Brandt, commanding the artillery observation post on the refinery's third floor, had spent the previous evening studying American engineering doctrine with the thoroughness of a doctoral candidate. The 26-year-old former mathematics teacher had calculated that visible American truck traffic suggested a bridging attempt might occur within 48 hours, but probably not until American infantry secured the eastern bank through conventional assault operations. His calculations were impeccable, based on correct data, analyzed through proven methodologies. The only problem was that his calculations assumed American engineers would follow German doctrine regarding bridge construction, an assumption about to be shattered by combat engineers who had learned different lessons from different traditions. At 06:45, Hoffman watched American engineers begin unloading equipment from their trucks. Through his binoculars, he could see Bailey Bridge panels being stacked near the riverbank in organized rows. The activity seemed consistent with preliminary construction preparations, exactly what German doctrine would predict for the initial phase of a multi-day bridging operation. What he couldn't see, because his education had never covered it, was that these weren't preparations for construction. This was construction itself, already beginning, performed by men who had practiced these exact movements hundreds of times until they could execute them while exhausted, under fire, and in darkness. The 291st Engineer Combat Battalion had arrived at the Ruhr with experience that no German engineering unit possessed. They had built bridges across the Moselle under artillery fire, replaced destroyed Rhine River crossings while German aircraft strafed their positions, and learned through brutal trial that speed was survival in combat engineering. They didn't follow German doctrine because German doctrine would have gotten them killed months ago. Staff Sergeant Robert Murphy, 32 years old, from Pittsburgh, Pennsylvania, had worked construction before the war. He understood load calculations and structural engineering from building steel frame buildings in a city where unions demanded perfection and bosses demanded speed. The army had taught him military engineering doctrine, then combat had taught him to forget half of it and improvise the rest. Murphy's crew of 12 men could assemble a Bailey Bridge panel in 3 minutes and 40 seconds, less than half the time German doctrine considered theoretically possible. They achieved this speed not through superhuman effort, but through choreographed teamwork, where every man knew his role so thoroughly that conscious thought became unnecessary. They moved like assembly line workers because that's what they were, factory workers and construction hands who brought civilian efficiency to military engineering. The German assumption that bridge construction required specialist expertise was technically correct but practically misleading. American engineer battalions were filled with men who had built factories, erected skyscrapers, and installed industrial equipment before the war. They weren't learning engineering from military manuals. They were applying existing skills to military problems using methods developed through American industrial practice rather than European military tradition. At 0700 hours, American engineers began driving the first foundation piles into the riverbed. Hoffman watched with professional interest, noting that they were using pneumatic hammers powered by portable compressors, equipment that German engineers typically employed only in rear area construction projects, not combat operations. The Americans were using the hammers while under sporadic machine gun fire, an approach that seemed reckless until you understood their calculation. Working under fire was dangerous, but so was working slowly. American engineers had learned that accepting 5% casualties during rapid construction often meant avoiding 50% casualties during prolonged operations. This was fundamentally different mathematics than German doctrine taught, and it produced fundamentally different results. The foundation work continued for 30 minutes, while German machine gunners took intermittent shots at exposed workers. 3 Americans fell wounded, evacuated quickly by medical personnel, who seemed to anticipate casualties as routine construction costs, rather than signals to halt operations. This acceptance of risk as a normal engineering parameter would have seemed insane to German doctrine writers, but it reflected hard lessons learned from months of combat, where hesitation killed more men than boldness. By 0730, the foundation piles were in place, and American engineers began positioning the first Bailey Bridge sections. Hoffman expected this process to take hours based on his understanding of proper assembly procedures. Instead, he watched panels being swung into position, connected, and secured in minutes rather than hours. The Americans were moving like circus performers, not military engineers, working with practiced synchronization that suggested extensive rehearsal. What Hoffman couldn't know was that every man in the 291st had built at least 20 Bailey bridges during training exercises at Fort Belvoir, Virginia. They had practiced in daylight and darkness, good weather and storms, under simulated artillery fire and actual harassment from training cadre who made their lives miserable to prepare them for days exactly like this one. The repetition had burned the procedures into muscle memory until bridge building became as automatic as breathing. German military culture emphasized individual expertise and officer supervision. American military culture, reflecting its industrial origins, emphasized standardized procedures and team coordination. German engineers waited for officer direction before acting. American engineers had sergeant-led crews who executed predetermined procedures without requiring constant supervision. This doctrinal difference meant American engineering units could operate faster because they required less coordination overhead. At 0800 hours, the bridge deck was 20 feet long and growing visibly with each passing minute. Hoffman realized with growing unease that the Americans were achieving construction speeds that shouldn't be possible according to every calculation he had learned. He called for artillery fire on the growing structure, and within minutes, German 105mm shells began falling near the American construction site. The Americans didn't stop working. They adjusted their positions, used smoke grenades to obscure German observation, and continued assembly operations even as shell fragments pinged off steel panels and threw up geysers of mud from near misses. This was the moment when German assumptions collided with American reality. The bridge construction wasn't slowing under fire, it was accelerating. The artillery barrage that Lieutenant Hoffman had called down represented everything German doctrine promised would stop American engineering operations. 12 guns of the 3rd Artillery Regiment fired in coordinated volleys, dropping high-explosive shells in a pattern calculated to cover the entire American construction zone. The mathematics were sound. Each shell had a kill radius of 40 feet. 12 shells per minute meant complete coverage of a construction area, measuring 200 feet by 100 feet every 90 seconds. But mathematics required certain assumptions to produce predictable results. German doctrine assumed that construction crews would seek cover during artillery bombardment, halting work until fire lifted. American engineers had learned different calculations through months of combat. Stopping work meant extending exposure time, which meant more total casualties than accepting losses while maintaining momentum. Sergeant Murphy's crew worked through the barrage with movements that looked suicidal to German observers but reflected careful risk assessment. They positioned equipment to provide blast shields, used natural depressions for momentary cover, and maintained construction rhythm that kept the bridge growing even as shells exploded close enough to shower them with frozen mud and steel fragments. Private First Class James Chen, a 23-year-old from San Francisco who had worked as a welder in the Richmond shipyards, connected panel joints while crouched behind a partially assembled section that provided minimal protection from shell fragments. His hands moved with mechanical precision, learned from connecting ship hull plates under similar time pressure when production quotas demanded impossible speed. The difference was that shipyard supervisors didn't kill you for missing deadlines, just fired you. German artillery had more permanent consequences for mistakes. By 0830, the bridge extended 60 feet from the western bank, despite 15 minutes of concentrated German artillery fire. 3 American engineers had been killed, 7 wounded, but construction continued without pause. Medical corpsmen dragged casualties to aid stations while replacement workers moved forward to fill gaps in construction crews. The system worked because it had been designed to absorb casualties without halting operations, a concept that violated German doctrine but reflected American industrial practice where production lines continued regardless of individual worker absences. Hoffman watched through his periscope as the bridge sections extended across the river with speed that seemed to violate physical laws. His engineering education told him this shouldn't be possible. Bailey bridge panels required precise alignment, secure connections, and careful testing before bearing weight. The Americans were achieving alignment through eyeball estimation, securing connections with rapid hammering rather than careful inspection, and apparently skipping testing procedures entirely. What German doctrine classified as recklessness, American practice understood as calculated risk. The Bailey Bridge system's modular design included built-in redundancy. Each panel could support loads far exceeding design specifications. Connection points had safety margins that allowed imperfect installation to still achieve acceptable strength. The British engineers who designed the system had anticipated field conditions where perfect installation was impossible, building forgiveness into the structure itself. American combat engineers had learned to exploit this forgiveness through experience that German engineers, working primarily in rear areas with proper equipment and adequate time, never acquired. They understood which specifications were critical and which were conservative safety margins that could be compressed under combat necessity. This knowledge came from building dozens of bridges under fire, learning through survival which shortcuts killed you and which ones just looked dangerous to observers who hadn't tried them. At 0900 hours, German machine gun positions opened sustained fire on the bridge construction crews. Tracer rounds carved orange lines through morning air, concentrating on clusters of workers who presented obvious targets. The MG-42 positions had been pre-registered on likely construction zones, allowing German gunners to deliver accurate fire without extensive aiming procedures. The Americans responded with smoke grenades that created artificial fog banks along the riverbank, obscuring German observation while allowing American engineers to continue working through practiced coordination that didn't require visual contact with adjacent crews. Sergeant Murphy directed his section by shouting commands that had been rehearsed until every man knew exactly what Section 3, Advance and Connect, meant, without requiring detailed explanation. This was another doctrinal difference that German observers couldn't fully appreciate. German military culture emphasized written orders and precise communication. American military practice, influenced by industrial shop floor experience, relied on verbal shortcuts and understood context. German engineers required officer direction for each construction phase. American engineer sergeants had authority to execute entire operations using pre-approved procedures that didn't require waiting for command decisions. The bridge continued growing. 70 feet, 90 feet, 110 feet. Each section represented hours of German calculation compressed into minutes of American execution. Hoffman found himself recalculating construction rates multiple times, unable to believe his initial observations. At current progress rates, the Americans would complete the bridge before noon, achieving in 5 hours what German doctrine insisted required 3 days minimum. Lieutenant Brandt, in his artillery observation post, was experiencing similar cognitive dissonance. His mathematics education told him the construction speed was impossible, yet his eyes reported bridge sections extending across the river with mechanical inevitability. He called down additional artillery fire, redirecting 2 more batteries to concentrate on the growing structure itself rather than the prothing, construction crews. German 105mm shells began impacting directly on completed bridge sections at 0930. High explosive rounds, designed to destroy fortifications, struck steel panels with violent impacts that should have demolished the structure. Instead, the bridge absorbed the hits with damage that looked catastrophic but remained structurally functional. Panels bent but didn't break. Connections loosened but didn't separate. The redundant design that British engineers had incorporated proved its worth as damaged sections continued supporting loads, while adjacent panels compensated for reduced strength. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. American engineers responded to the direct fire by accelerating their construction pace rather than seeking cover. This counterintuitive behavior reflected hard-earned understanding that artillery couldn't stop bridge construction fast enough if crews maintained momentum. The mathematics were brutal but clear. Each shell might damage 10 feet of bridge structure. American crews were adding 20 feet of new construction every 10 minutes. Artillery was losing the race against construction speed. German observers, watching this through the lens of their doctrinal training, interpreted the American behavior as fanatical determination rather than calculated strategy. The possibility that American engineers had developed systematic methods for working under fire, methods based on industrial efficiency rather than military tradition, didn't occur to German analysts because such methods violated everything they understood about proper engineering practice. By 00:10 hours, the bridge extended 140 feet across the 180-foot river. American engineers were working in water now, driving foundation piles into the riverbed while standing waist-deep in current cold enough to cause hypothermia in minutes. They wore inflatable life vests that provided minimal protection against drowning, but no protection against German machine gun fire that occasionally found targets among the exposed workers. Private Robert Henderson, a 19-year-old from Minnesota who had worked his father's dairy farm before the war, hammered foundation bolts while water that felt like liquid ice soaked through his uniform. He had fallen through frozen pond ice twice as a child and learned that cold water killed through action rather than hesitation. Keep moving, keep working, and get out before your body temperature dropped below functional levels. The principle applied equally to Minnesota ponds and German rivers. The final 40 feet of construction occurred at 00:10:30, with American engineers connecting the eastern bank section to the main span, while German artillery fire intensified to desperate levels. Shells fell in patterns that should have been impossible to work through. Yet the construction continued with momentum that seemed to defy both physics and military logic. At 00:11:15, 9 hours and 45 minutes after American artillery had announced the operation's beginning, the first Sherman tank rolled onto the western approach of the completed bridge. The structure flexed under 35 tons of weight, settling into final load-bearing configuration as additional weight-compressed connections and distributed stress through the entire span. The tank crossed at careful speed, reaching the eastern bank at 00:11:23 without incident. Hoffman watched this through his binoculars with emotions that mixed professional disbelief and tactical horror. The bridge that German calculations insisted required 72 hours had been completed in less than 6 hours of actual construction time, despite artillery fire that should have destroyed it multiple times, machine gun fire that should have killed enough workers to halt operations, and weather conditions that German engineers would have classified as prohibitive for major construction work. The second Sherman tank crossed at 00:11:30, followed by a third at 00:11:37. American infantry began moving across in company strength, using the bridge deck as a 3-lane highway that transformed the Ruhr from impassable barrier into minor tactical inconvenience. Within 30 minutes, 2 full battalions of American infantry occupied positions on the eastern bank, establishing a bridgehead that German doctrine had assumed would require weeks of fighting to achieve. German defensive positions that had been carefully sited to delay American river crossings suddenly found themselves outflanked by armor that shouldn't exist on the eastern bank for days. Machine gun nests oriented to cover western approaches became vulnerable to American tanks, attacking from unexpected directions. Artillery, positions that had pre-registered fire on western bank assembly areas, were now receiving counter-battery fire from American forward observers who had crossed the bridge and were calling down destruction on German guns. The cascade of tactical failures accelerated throughout the morning. German reserves positioned to counterattack expected American bridgehead attempts arrived at positions already overrun by American armor that had crossed before German commanders even realized a bridge existed. Communications networks that assumed days of warning before American tanks could cross began breaking down as contradictory reports flooded command posts with information that seemed tactically impossible. By noon on December 16, 1944, American forces controlled both banks of the Ruhr at this crossing point, with armour and infantry flowing across the completed bridge at rates exceeding 200 vehicles per hour. The defensive line that German planning had assumed would hold for 2 weeks had been breached in 6 hours through engineering capabilities that violated every assumption German doctrine contained about American operational capabilities. Part 3. 2. The cost of truth. The interrogation room in the American prisoner of war facility at Aachen was cold on December 18, 1944. Lieutenant Karl Hoffmann sat across a wooden table from Captain Robert Wilson of Army Intelligence, trying to explain how German defensive calculations had failed so catastrophically at the Ruhr crossing. Wilson had engineering degrees from MIT and spoke fluent German, making him ideal for technical interrogations of captured German officers. He found Hoffmann's testimony fascinating not because it revealed German secrets, but because it revealed German assumptions. The belief that American engineers would follow European military doctrine, the certainty that proper bridge construction required specific timeframes, regardless of circumstances. The conviction that industrial shortcuts inevitably produced inferior results. "Your calculations were correct," Wilson told Hoffmann in precise German. "Bailey Bridge construction does require 72 hours under the conditions you described. The problem is that American combat engineers don't construct Bailey bridges under those conditions. They've developed different methods based on industrial practice rather than military doctrine," Hoffmann struggled to understand. His engineering education at Technical University of Berlin had been rigorous, comprehensive, and completely inadequate for predicting American engineering behavior. The Americans had trained their combat engineers like factory workers, emphasizing speed and standardized procedures over individual expertise and careful preparation. The approach seemed to violate fundamental principles of proper engineering, yet it produced bridges that worked. The interrogation reports from Hoffmann and 43 other captured German officers revealed a pattern of systematic misunderstanding about American capabilities. German intelligence had accurately documented American equipment, correctly assessed American training standards, and precisely calculated American construction timeframes. But every analysis had assumed Americans would employ that equipment and training according to European military principles that emphasized careful preparation over rapid execution. The 291st Engineer Combat Battalion had built the Ruhr Bridge in 9 hours and 17 minutes of total elapsed time, including 6 hours and 42 minutes of actual construction work. German doctrine insisted such speed was impossible. American industrial practice proved German doctrine wrong through methods that prioritized team coordination over individual expertise, accepted casualties as construction costs rather than signals to halt work, and compressed safety margins to limits that horrified European engineers but reflected calculated risk assessment based on combat experience. The battalion's casualty list told its own story. 11 men killed, 29 wounded during construction operations. These losses seemed catastrophic by German engineering standards, where proper preparation was supposed to minimize casualties. American combat engineers understood different mathematics. Those 40 casualties enabled 2,000 infantry and 50 tanks to cross the Ruhr without fighting for the bridgehead. The exchange ratio was brutal but effective. Sergeant Robert Murphy received the Silver Star for his role in the bridge construction, though he later said the decoration felt strange for work that resembled his pre-war construction job more than traditional military heroism. His crew had built the Ruhr Bridge using techniques developed building factory expansions in Pittsburgh, where contractors faced penalty clauses for late completion and unions demanded safe but efficient procedures. The bridge itself stood for 3 weeks before German artillery finally destroyed it on January 7, 1945. By then, the 291st had built 4 more bridges across the Ruhr, each completed in under 12 hours despite German efforts to prevent their construction. American engineering battalions across the Western Front were achieving similar results, transforming rivers from barriers into inconveniences through industrial efficiency applied to military problems. German military analysis of the Ruhr crossings, conducted in January 1945, concluded that American engineering capabilities had been systematically underestimated throughout the war. The analysis recommended updating German doctrine to account for American methods, but by that point German defensive capabilities had collapsed to the point where revised doctrine made little practical difference. The broader lesson, recognized by post-war military analysts on both sides, was that American industrial culture had produced military capabilities that European military tradition couldn't predict or counter. Combat engineers trained like factory workers, supplied through logistics systems designed like civilian supply chains, and employing equipment standardized for mass production rather than custom engineering, had defeated German forces, trained in centuries-old military traditions that emphasized individual expertise and careful preparation. Private James Chen survived the war and returned to the Richmond shipyards, where he worked until retirement in 1979. He rarely spoke about his engineering work in Germany, though he once told his grandson that building bridges under artillery fire wasn't much different from welding ship hulls under production deadlines. "Same principle," he said. "Keep your head down, do your job, and trust your crew knows theirs." The 291st Engineer Combat Battalion was deactivated in 1946 after building 143 bridges across European rivers and reconstructing over 800 miles of roads destroyed by retreating German forces. Their speed and efficiency became the standard for American combat engineering, incorporated into doctrine that emphasized rapid construction using industrial methods rather than traditional military engineering approaches. Lieutenant Wilhelm Brandt, the German artillery observer who had calculated American construction timeframes with mathematical precision, spent 3 years in Allied prisoner-of-war camps studying American engineering manuals. After his release in 1948, he wrote a dissertation comparing German and American military engineering doctrines. His conclusion was that both approaches were technically correct, but American methods were doctrinally revolutionary. "The Americans didn't defeat German engineering through superior calculations," Brandt wrote. "They defeated us by refusing to calculate the same things we calculated. Where we measured precision, they measured speed. Where we emphasized individual expertise, they relied on team coordination. Where we prepared carefully to minimize risk, they accepted risk as the price of rapid execution. We couldn't counter their methods because we couldn't imagine military engineering working that way." The Ruhr River Bridge became a case study at American military engineering schools, taught not as an example of superhuman courage, but as a demonstration of industrial efficiency applied to combat conditions. The lesson emphasized was that combat engineering wasn't fundamentally different from civilian construction work. The same principles that built factories and skyscrapers could build tactical bridges, if engineers understood that speed had tactical value worth accepting increased risk. German prisoners working on reconstruction projects in American-occupied zones were shocked by American construction methods that seemed to violate basic engineering principles, yet produced functional results faster than proper German procedures. The cultural collision between careful German craftsmanship and rapid American efficiency continued for years after the war ended, reflecting fundamental differences in how the two nations approached technical problems. By the time the Cold War began, NATO engineering doctrine had absorbed American industrial methods while maintaining European emphasis on structural quality. The synthesis recognized that both approaches had value. German insistence on proper preparation prevented catastrophic failures. American emphasis on rapid execution enabled tactical flexibility. Modern military engineering combined both traditions into doctrine that emphasized speed when necessary, precision when possible, and realistic assessment of what each situation actually required. The bridge at the Ruhr was dismantled for scrap metal in 1947, its steel panels recycled into reconstruction projects across war-damaged Germany. No monument marks the location where American engineers achieved what German calculations insisted was impossible. But the lesson lived on in military doctrine and engineering schools, where students learned that assumptions about how things must work often blind observers to how things actually do work. The mathematics of impossibility had been recalculated by combat engineers who brought industrial efficiency to military problems, proving that the fastest way to build a bridge wasn't always the way engineering textbooks prescribed. Sometimes it was the way factory workers improvised when deadlines mattered and supervisors weren't watching. Sometimes proper military procedure was less important than getting the job done before the enemy figured out what you were doing. 9 hours to build a 600-foot bridge. 11 men killed, proving German doctrine wrong. 40 casualties, total enabling thousands to cross a river that was supposed to remain impassable for weeks. The arithmetic was brutal, but it was also revolutionary, demonstrating that industrial methods could transform military operations if commanders were willing to accept that construction workers might understand engineering better than military academy graduates. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.